Okay, so this is just going to be a short review over concepts and probably some helpful things to put on your note card for your exam on Wednesday. All right, so I think one of the first things we did after exam three was look at orbitals and like their shapes and everything like that. So in terms of orbitals, um, I guess something you should know is the shapes of them and then how many or what different types of orbitals can exist at what energy level. So at n equals 1, it's just the s orbital. N equals 2, it's going to be s and p. N equals 3, we have sp and d. N equals 4. Um, I think n equals 4 is sp, d, and f. But remember, there's certain rules for for electron configurations, which we'll get to in a second. But let's say we're dealing with something in the n equals 4 shell. Like we have, I don't know, let's just pick gallium. So we have an argon core, and we'll go over this in a second if anyone is still unclear on how to write electron configurations. But we've got an argon core, and we've got 4s2, and then a 3d10. And then what were we doing? I think we were doing gallium. And then we have a 4p1. And remember that though this 3d10 does exist, um, like with the 3 in front of it means that it's in the third energy level. You don't actually see these start popping up until the fourth one. And then for, let's just say an even larger one, I guess. Um, I think it's whenever we start getting to like the sixth energy level or something like that is when we actually end up with these f orbitals. But there shouldn't really be anything like that on the exam. But just for practice, let's do, I don't know, lead. So lead has a xenon core, and then oops, we have 6s2, um, 5d10, and then 4f14, and then we get to 6p2, which is where lead is in the sixth row in the second, I guess, electron in the p section. So yeah, just remember these rules about the d and 10. D orbitals will be, I guess, one n or one number less than like the s or p orbitals, and then f orbitals will be two numbers less than whatever six and the p orbitals are. Um, and then the shapes of orbitals. So s orbitals are just going to be the really simple ones where you have it's just a circle. That's all. That's the most optimum, I guess, configuration to set up those two electrons that can exist in that. And then so that's for S, and then for P, you have something like this, where you have kind of like the dumbbell shape ones, where you have something like this, and then just think of each one of those dumbbell shapes lying on one of the axes of X, Y, Z. Um, and then the d orbitals, this is where it starts to get super funky. And you shouldn't have to like draw these or anything like that, but you should know, I guess, what they look like. Um, God, yeah, these are really hard to draw. There's like it's like four little like lobes, I guess, like kind of connected to the origin. And there's also an orientation for d orbitals where you have something like a kind of ring right there, and then two lobes right here. It's yeah, it's really wacky, and you shouldn't really have to remember anything above that, but just remember that this is just like a sphere. Oops. A sphere for s orbitals, dumbbells for p orbitals, and then d orbitals is just whatever. Yeah. Okay, and then I guess one of the nice things we do is uh, electron configuration slash noble gas notation. All right, so for electron configuration, you really just have to know what orbitals exist at each energy level, and then how many electrons fit into one of those. So let's just say we pick phosphorus at random. It has 15. It has 15 electrons total, and it exists at the n equals 3 energy level. So we can just start filling up orbitals, yeah, until we get to 15. So we start with 1s. You start with s in every single energy level. So 1s2, there can be two electrons in each orbital for any orbital for any energy level. Okay, and then we're done with the first energy level, and then we go to the second one. We have 2s2, another 2 electrons, and then we have 2p6 because there's 3 p orbitals, 2 electrons in each, so that's 10 total that we've used. And then we go to 3s2, that's 12, and 3p3, and we've used all our 15 orbitals, or 15 electrons filling up to the 3p orbitals. Okay, and then shorthand, I guess, for electron configurations, if you don't want to write everything out, you can just start at, um, you can start at, I guess, with the last completely filled n equals whatever level, and then continue on from there. So with this, we see that the 1 and 2 are already completely filled up, and that corresponds to uh, the gas neon. These are called noble gas notations because you always start with a noble gas. Um, so yeah, we start that, and then we just do 3s2, 3p3, and that means the same thing as what we have up here. Um, and then another thing, I guess, that we can go over are like the rules for filling up orbitals. So let's do something smaller. So let's do oxygen. So the electron configuration for oxygen is going to be 1s2, 2s2, 2p4. Okay, yeah, total of 8 electrons. That makes sense. All right, and then if we want to look at how like you go about filling up these orbitals, I guess. So we have this 1s, and then we have this 2s, and then we have the 3p orbitals from this 2, or from the n equals 2 energy level. All right, and this is another rule to have on your exam, is that the first thing we start with is the Aufbau principle, which states that whenever we're filling up these orbitals, the electrons will always go in the lowest energy level first, which is the 1s in this case, or it'll be that way for every single atom. So we start filling up orbitals like this, and then the next thing we encounter is the Pauli exclusion principle, which means that no 2 electrons can have the same quantum numbers, which basically means that you can't have anything like this, because that would mean that they're in the same orbital, in the same energy level, and they have the same spin. Remember, that spin is either positive 1/2 or negative 1/2, and that just can't exist. So then, due to Pauli exclusion principle, we have to have a spin up and a spin down. Um, okay, yeah, and then we can do the same for filling up this one. And remember that we have to fill the lowest energy levels first before we can go to the higher energy orbital. So that's why we fill the 2s before the 2p. And then the last rule we come into is called Hund's rule, or Hund's rule. I don't really know how to pronounce that, but we see that we've used 4 electrons and we have 4 left. And what Hund's rule says is that each orbital has to be singly occupied before one can be doubly occupied. So you can't have something like fill up this, then this, then this, then this, because due to how these electrons interact with each other, it's actually a lower energy, and a more stable configuration if these orbitals are filled by themselves first, and then started to add the extra ones. So then in that case, we need to go one here, one here, one here, and then we can finally add this last one to finish off filling our orbitals. So that's kind of the process you want to go through, and those are the three rules you should know: Aufbau principle, Pauli exclusion principle, and Hund's rule. Um, and then another thing we can go over is like the special stabilities. Um, so I guess one like easy way you can think about this is that I guess we've rarely been seeing molecules where we have helium or neon or argon or krypton as the central atom, or in any molecules at all, just because noble gases are really, really stable. And we can look at this by examining their electron configurations. So if we look at the electron configuration of, let's say, neon, um, that is going to be 1s2, 2s2, 2p6. Yes, 2p6. That's 10 total. And if we do the same thing, we start filling up orbitals. So this the special stability that comes with a noble gas can be explained due to filling up the orbitals. We see that every single orbital is completely filled. Um, and yeah, that's just a rule. Whenever things are completely filled, they're just extra stable because there's nothing like to react. Like let's say you're in a reaction or like with like a Cl minus a chlorine anion. The chlorine anion is going to want to react to gain an electron to make it that full octet. But because this octet of neon is already filled, it doesn't have to um, it doesn't want to gain any more electrons, so it's fine just existing by itself as an inert gas. Um, and then another rule of stability we can remember is half-filled orbitals. So I think it's um, let's just do like nitrogen or something. So that one is going to be 1s2, 2s2, and then 3p3. Fill these orbitals again. There is so there is like a special I don't know, stability that comes with just half-filled orbitals. Um, and yeah, I think these are just more stable than something, let's say like this or this. Um, Partly probably because there are less electrons to have like electron repulsion, but probably also because um, yeah, I don't know. I'll get back to that. But yeah, just remember those. Um, okay, and then the next thing we started to look at was the periodic trends. Um, okay, so let's see. Like that one worksheet we had where we had Z effective, the periodic trend um, is going to be increases uh, across a row, and yeah, and we saw that with the worksheet where we had sodium on the very left had um, an effective nuclear charge of 1, and then argon had an effective nuclear charge of 8, I think. And this basically just means that the outer electrons are going to be held more tightly because if you guys remember Coulomb's law, you had K, or let's just rewrite this: 1/4 4 pi uh, permittivity of free space, Q1 Q2 over R squared. Um, and like I guess explained in the mock exam video, we can kind of treat this charge as the nucleus and this charge as the electrons. And whenever that charge in the numerator, whenever that charge product is greater, there's going to be a greater interaction between both of the charges, being the nucleus and the electrons, specifically the valence electrons. So then that means whenever Z effective is greater, that means that the outer electrons are held more tightly, and that explains, or that can explain um, another rule I guess we can get on is ionic radius, or atomic slash ionic radius, and specifically right now the atomic radius. So just like we said that as the effective nuclear charge increases, the valence electrons are held more tightly, which means that they're going to be physically pulled closer to the nucleus. So it's kind of like um, a similar trend with Z effective, which means that it increases across a row, and we already explained that. And then also it put this in terms of decreasing, and decreases going down. And that can just be thought of like very intuitively, like as you go down, the energy levels increase, which means that there are more orbitals and they're more farther, or they are just farther away from the nucleus. So that means you're going to have um, just a greater size as you go down a column. Um, and I accidentally messed up that. I had it right the first time. The atomic size will increase going down a column. And then if we look at ionic radius, let's consider something like we can do Na and Cl in the same n equals 3 row. So if we see that Na, the ion that's going to form is Na plus. Um, and whenever sodium forms the sodium ion, it's going to lose an electron, and you're no longer going to have that one single electron in the n equals 3 level. You're just going to have um, noble gas core just going up to neon, and you won't have anything in the n equals 3 energy level, just the 1 and 2. So this means that positive ions or cations are going to be smaller, and then we see something like Cl, chlorine. When this forms the chlorine anion, we know that the negative sign, this charge right here, means that it's going to gain an electron. It's going to completely fill that very last orbital, and we know that whenever there are more electrons, there's more electron-electron repulsion, which means that the electrons are going to want to be farther away from each other to be more stable, which means that the actual size of the ion will be greater if it's an anion, which is just a negative ion. Okay. I guess another trend is going to be ionization energies. The only thing I guess you really need to be able to discern, I guess, is given like a set of ionization energies 1 through 3 or 4 or 5, and look out for the jump. And whichever number ionization the jump is at, subtract 1 from that number, and there will be, and that's how many valence electrons there are. And you can look at the periodic table and discern what what atom it was. So if we look at something like, and this is on the mock exam, um, let's not say it's aluminum, but it is aluminum. So let's just say, like, let's make up some numbers. I1 is equal to 100, I2 is equal to 200, I3 is equal to 300, and then I4 is equal to, I don't know, 10,000 or something crazy. like just a very large apparent jump. So in this, we see that it took three ionizations before the jump. And the way I think about this is that uh, the ionizations before the jump was just taking away from the very valence shell, which are held not as tightly as the core electrons. And then once you get to that jump, that's when you're starting to take from the core electrons. So the first whatever amount before before the huge jump will be how many valence electrons there actually were. And in this case, there were three. And then in the fourth one, we had a jump. And then if we look at something like aluminum, which is what we're representing here, or anything in the third row, or the row 13, column 13 of the periodic table, um, we can see that Al, just normal, is going to be, start with this noble gas notation, and then 4s2, oops, 3s2, 3p3, 3p1, okay, and then aluminum plus is going to be Ne3s2, and that's it, because we took away that one from the p orbital. And then Al2 plus is going to be neon 3s1, and then Al3 plus, which is the common ion for aluminum, is just going to be Ne, and then 3s0 or nothing, just to denote that. So you see that this is ionization 1, 2, 3, and then once we get to that fourth one, which would just be, I don't know, Al4 plus, this is going to be something like, we start at helium now, because we're going into that second energy level, and then we'd have 2s2, 2p5, right? Because having this here is the same thing as like just ending at, if you're starting at helium, ending with 2p6, and we took away one. So this means that we're now pulling into these core electrons, which we weren't showing in these over here. So yeah, just look out for that jump, and however many ionizations it took to get to that jump is how many valence electrons exist for that atom, and then you can just look at the rows in the periodic table or the columns and see what that would be, and then match that to the answer that are given. Okay, another one is metallic character. And the metallic character, the trend is really just more metallic to left and down on the periodic table. And you can like physically see this on the periodic table. Like let's say we take um, column 14. We start with carbon, then silicon, then germanium, then tin, then lead. So we start with carbon here. We have a nonmetal, and then we get to silicon and germanium. Those are metalloids, and then we get to tin and lead, and those are metals. And you can do the same thing for pretty much any row. At least like on that right side, you can see a clear trend. And yeah, and just know that metallic character means like just kind of like the more metallic something is, the more likely it is to form a cation, like to lose electrons. Um, yeah, that's pretty much it. Um, and then I guess also for this last trend, electronegativity, we know that the trend is going to be more electronegative um, to right and up. So trend is like this, and there's that arrow. So the most electronegative are going to be over here. Least are going to be somewhere down here, like at the metals like francium and radium. Um, Let's stay up. Yeah, and I guess just also be aware to um, I guess like qualitatively determine like what the differences between some electronegativities are. So something like an F bond, those have the same electronegativities, so there's no difference. That's going to be a completely covalent bond. But then if you have something like um, NaCl, that is something that is completely metallic, and it's something that is completely nonmetal, and that's going to be a huge electronegativity difference because Cl is Cl. Oh my goodness. Cl is somewhere over here, and then Na is somewhere over here. Huge difference. And yeah, and then this would be like an ionic bond. This is going to be a covalent bond. Just stuff like that. Um, yeah. Okay. Going on to the next thing. This is going to be, I guess, the first part of bonding. Um, Knowing how to draw Lewis dot structures. Um, let's just a very common one that we see very often. NH3, the Lewis dot structure is just going to be yeah. So that's going to be something like we have nitrogen as our central atom because we want something that's either more electronegative, or we want something that just kind of makes sense. And we know that. I guess another thing I forgot to point out uh, for the octet rule. Um, I will get to that. Okay, so we have H, 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 and we have two lone pairs up here. Um, so yeah, just kind of like the rules of like the first thing you do is like skeletal structure. Um, then assign lone pairs to terminal atoms. Um, and then just kind of and then just balance everything to see what works. And yeah. And remember, I guess I forgot to write that, but count your valence electrons, and that's how you know how many electrons you have to play with to actually draw the Lewis dot structure. And then another thing, what I was about to say earlier is the octet exceptions. So when n equals 3 or greater, when you're in the third energy level or greater, the octet can be expanded. And this is like what we've seen in some of the worksheets where you have something like xenon tetrafluoride, where you have like two lone pairs and four bonds for the central xenon, which is a total of I'm blanking, which is like 12 electrons on it. So yeah, it's just stuff like that. Just be aware that those things can exist. Um, and then if you're not in n equals 3, then you can't expand that. Um, so yeah, so anything in like n equals 1 or 2 are just going to be just 8. And then another thing, duet rule. Hydrogen is always terminal, which means that it's always going to be like somewhere over here, like on the ends. It's never going to be the central because it can only have one bond. And it'll never have lone pairs or anything like that. And then some other exceptions I think we saw were boron and aluminum can have shrunk octets, I guess. Um, and this is like what we saw. I think there's like we saw with like AlCl3. Uh, AlCl3. We saw that one was just going to be um, and that's the entire structure. Aluminum is just fine with only having three bonds or six electrons in its valence shell, and the same thing with boron. Um, Okay, and then some trends with with bond energies. Um, uh, I guess just like knowing differences between, let's just say, like a carbon single bond, carbon double bond, a carbon triple bond. I don't even know if that exists, but um, let's say like this will be the shortest, this will be the longest, um, in terms of bond lengths, and then this will also be the strongest bond, and this will be the weakest bond. And like, I mean, and that's like pretty intuitive. There are more electrons holding these two things together. And there's some overlap orbitals. Like, there's that one sigma bond, obviously, in each one of these types of bonds. But then there's like in the double bond, you've got one pi bond, and then in the triple bond, you've got two pi bonds, which means even more overlap of p orbitals. Um, Stuff like that. Um, know that bond breaking is endothermic, right? Because you measure the strength of bonds by putting enough energy and seeing how much energy it takes to break that bond by kind of like overloading the bonds you can think of. And then bond forming is exothermic. And you can think of this as like if you were in the process of like overloading a bond, putting a bunch of energy into it to break it, um, whenever you form something to create a more stable molecule, it's going to expel a bunch of that energy to form that stable molecule. Um, Remember that, I guess, if you're calculating delta H, it's going to be equal to bonds broken minus bonds formed. And it's kind of hard to get used to because pretty much everything you do, and like with delta H and next semester, if you take chemistry 2 with like Gibbs free energy and entropy, it's going to be final minus initial or products minus reactants. But in this case, because the bond energies are positive, you're going to want to do this in bonds broken minus bonds formed. So it's going to be the energy of the reactants minus the energy of the products, and that'll give you um, the number that you're supposed to get. Um, Formal charges. We saw this on the mock exam just a little bit. Formal charges. And formal charges are going to be used to, I guess, to evaluate which structures, which resonance structures are going to be the best for a Lewis dot structure. So, can't think of something right now. Let's just do like CO2. Let's see if we can figure something out like this. Um, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so yeah, we use 16 total. We use, which is how many valence electrons are available to us, 12 from the both oxygens and then 4 from the carbon. Um, and we use formal charges to evaluate how good a Lewis dot structure is, or like how likely that form of the molecule is to exist in nature because it's more stable. Um, and it's just going to be valence minus dots minus lines for each atom in a molecule. So if we start with carbon, we know carbon has 4 valence electrons and there's 4 dots connected to it, so that formal charge is 0. That's good. We want it to be 0 or as close to that as we can. And we see this oxygen over here has 3 lines and 2 dots, so that's going to be 6 minus 3 minus 2 is equal to 1. And then this oxygen over here has 6 minus 1 is equal to -1. And then another rule that we have to have is formal charges must add to charge on molecule or ion. So when we add these two together, we get 1 plus -1, and then that's just going to be 0. And CO2 is a neutral molecule; it doesn't have any charge, so that makes sense. We should get that. But this Lewis this Lewis dot structure isn't as optimal because we have formal charges. Anything that's other than 0. So if we draw something like this, which is how you'd see it, we see this one has 0, this one has 0, this one has 0, and then that's the best one we want. And if we do have something like NO3, let's say nitrate, we have a nitrate, oxygen. So let's see how many valence electrons we have. 18 from the oxygens, and then 5 plus 1 because the charge. So we have 24 total valence electrons. Right? 18 plus 5 is 23 plus 1 is 24. Okay, yeah, we have that. And let's start putting these things on. Okay, so if we evaluate formal charges, we see that this has -1, this has -1, this has -1, all the same, and then this has 5 minus 3 lines is 2. And when we add those two together, we get a formal charge of -1, which corresponds to this charge right here. So we know we're doing something right. But another one of the rules for formal charges is that we don't want formal charges on the central atom if we can help it. We want them on the more electronegative atoms, which in this case is oxygens. So I think we can do something like nitrogen, oxygen. So then on this one we have 0, and then we have -1, and then +1, and then that also adds up to -1, which makes sense. Okay, and then yeah, and it actually turns out that in this case we can't get the formal charge off of the central nitrogen. Yeah, but it's overall a better Lewis dot structure because instead of it on this one being a +2 charge, we have a +1 charge, and that's as best as we can do, with the charges still adding up to the ion, or to the charge in the ion, which is -1. So yeah, that's another rule. Want formal charges on more electronegative atoms. Okay, and then for this last, I guess, section that we've had in class, this one's just going to be like the geometries / VSEPR. I guess we can kind of make like a grid for this. Electron groups. Have one. Oops, not one. I guess yeah, we can have one. Or no, let's just, okay, 2, 3, 4, 5, 6. This one's going to be electron geometry. This one's going to be lone pairs, and this one's going to be molecular geometry. I guess we can do angles as well. Oh, that's angels. And then after this we can go over the shapes and stuff like that. Okay, so the electron geometry for something with 2 electron groups is going to be linear. With 3 electron groups around the central atom, it's going to be trigonal planar. With 4 groups, it's going to be tetrahedral. With 5 groups, it's going to be trigonal That's supposed to say bipyramidal. Okay, and then 6 groups is going to be octahedral. Okay, and then I think I set up this table wrong. Yeah, I think I did set this up wrong. Okay, so if you lone pairs don't really count for that one. And then I guess also the same thing for this. Yeah, because if something's going to be trigonal planar, then it can already have like a decreased octet, or it will just fill with just four types of bonds. Okay, so if we have a lone pair on tetrahedral, this one is going to be trigonal pyramidal. And then if they're, yeah, I really set this up wrong. It could be 1 or 2, and it can be trigonal pyramidal or bent. I don't think there can be 3. And then, okay, so if it's trigonal bipyramidal, you can have 1, 2, maybe 3. I don't know. But if there's one lone pair, it's going to be seesaw, and then if it's 2 lone pairs, it's going to be T-shaped. I don't think there's anything after that. And then for this one, I think it's the same as well, 1 and 2. If you have one lone pair on an octahedral electron geometry, you're going to have something that is square, pyramidal. And then if you have 2 lone pairs, then you'll have square planar. And then bond angles for something that is linear, you'll have 180 always. For trigonal planar, you'll have 120. For tetrahedral, you'll have 109.5, 107.5, 104.5, depending on how many lone pairs there are. For trigonal bipyramidal, you'll have 90 and 120, right? Because the shapes, because there's 3 equatorial atoms, which are trigonal planar, those are 120 apart, and then 2 axial atoms, which are 90 degrees from the equatorial atoms. And then octahedral is going to be 90 all around, because there are always or every single atom is always going to be 90 degrees from each other. Yeah. All right. Okay, so so for shapes, we have linear, which is just going to be like very very simple, something like that. And then we have trigonal pyramidal, which is going to be something like, I don't know, Z. And we don't have to use any of the wedges or the dash things, because these are all just still in the plane. And then we've got tetrahedral, which is going to be something like Z. I think it's like this. This the wedge that I drew really poorly. A, A, A. And remember that this wedge, the wedge denotes coming out of the page, and this little thing right here, this stripe thing, whatever this is going into the page. And then this is just going to be like a tetrahedron, right? If you flip it on any sides, it will be the same shape. It'll just be a tetrahedron with a triangular base. And then we've got trigonal bipyramidal, which is going to look like Z. It's going to be A, and then A. So these three center ones are going to be 120 degrees from each other. They're all in the same plane, and then these two top ones are going to be well, they'll be 180 from each other, but they'll be 90 degrees from each one of the equatorial atoms. So yeah, that's how the trigonal bipyramidal will look. And then octahedral is going to look kind of similar to trigonal bipyramidal. You'll have, I think I have something like that. And it's like just kind of this centerpiece right here. It's like a square in a plane. It's all in the same plane. And then these two axial atoms are the same thing, like trigonal bipyramidal, and then everything is going to be 90 degrees from each other. And then another thing to note is about, I guess, polarity of these. So starting with tetrahedral, if even one is uh is different, like from the other three atoms, or if it's a lone pair or something, it's going to be polar. And this is only nonpolar if every single one of these is like if every single one of the terminal atoms is exactly the same. Um, and then kind of similar with trigonal bipyramidal, but not really. So if these three atoms in the equator part are the same, and these two atoms on the axial parts are the same, then it's nonpolar. But if you have something like these two are some species, and this is different, then it's going to be polar. Or if it's like these are all the same, this is one thing, and then this is something completely different, that's going to be polar again. So for some of these, you just have to draw the Lewis dot structures and see the orientations. Um, and then the same kind of thing with octahedral. If all of these are the same, um, and these two at the axes are going to be the same, then it's going to be nonpolar. Um, if these are the same, these are the same, these are the same, then it's also going to be nonpolar, and it's the same thing like trigonal bipyramidal. If like I don't know if these are the same, but these two right here are different, then it's going to be polar. Or if these two are different, it's going to be polar. So another thing, or just like trigonal bipyramidal, draw the Lewis dot structures, see how everything is gonna look. Some of the last things. That's a D. Hybridization. This one's really just as simple. At least knowing the hybridization is just as simple as counting how many things are bonded to it. So if you have two things bonded to a central atom, um, then it's going to be sp. Whether and two things bonded, whether that means like a bond and like a triple bond in a lone pair, or any combination of that, it's going to be sp. If you have three things bonded, it's going to be sp2. Um, Again, and these are electron groups, not just bonds. So this could be like two separate types of bonds, and then a lone pair for this one right here. And for four groups, sp3, same thing, lone pairs or bonds. How many ever or however many things are connected. Um, you just kind of have to like know these, I guess. And remember that lone or like single bonds, double bonds, and triple bonds, those all count to just like one electron group connected to that atom. So a triple bond doesn't mean like there are three things bonded plus some other bonds and some lone pairs and stuff like that. If there are five things bonded, it's going to be sp3d. Six things bonded, sp3d d2. Yeah, and then I think looking back at the bonds again, this is the very last thing. A single bond is just going to have one sigma. A double bond will have one sigma and then one pi. And then a triple bond will have one sigma and two pi bonds. Yeah. So I hope that helps you guys. Kind of like a brief review of concepts if you forgot anything, and some good tips to put on your note cards. So yeah, good luck.